Today we are going to solve the problem 2.29 of Griffith third edition Introduction to Quantum Mechanics. The problem 2.29 is analyze the odd bound state wave function of for the finite square well. Derive the transcendental equation for allowed energy and solve it graphically. Examine the two limiting cases. Is there always an odd bound state? These are the question that has been asked. I have already derived this equation, transcendental equation, in my theoretical lecture on finite square well potential. I don't want to repeat it here. Please kindly refer my lecture on finite square well potential. Uh, and graphical solution, we are going to see it here. And examine two limiting cases. Is there always an outbound state? These are the questions to be addressed. So we have seen this finite square well potential between inside the box, that is from minus A to plus A. The potential is zero. Outside the potential is V naught. And here is a positive x direction inside the box. Here the wave function is psi1 and here it is psi2. And remember that here the wave function is after all negative. If it is psi1, then inside it is minus psi1, psi1 minus x. Here also we know the add solution psi minus x, psi of minus x is equal to minus psi x. After all, it is multiplicative factor that you have to keep it in your mind. So in my theoretical lecture, we have seen the valid wave function psi1 here inside the box at positive direction. So psi1 is equal to p cos kx. Psi2 here it is t e power minus kappa x. So for the wave function, uh, in order to have continuity, you must have psi1 is equal to psi2. So we have seen psi1 is p cos kx, which is equal to t e power minus kappa x. And it derivative must be also the same. That is, uh, psi 1 prime must be equal to psi 2 prime. So if you differentiate this, you will get minus k sine ka. Of course, this p is here. And if you differentiate the right hand side, you will get minus kappa e power minus kappa a. And of course, you have this normalization constant t. So if you divide 2, this is, let us say, this is equation 2 and this is equation 1. So if you divide equation 2 by 1, then this static sign automatically cancelled out. Then this PP will cancel out. Then K sine theta sine Ka over cos Ka is tan Ka. And if you divide 2 by 1, T will get cancelled and the exponential term also will get cancelled. You will get only kappa. So this is the uh, this is the solution for positive x direction. Similarly, for negative x direction, this is very important because you have been asked, is there always an add bound state? So this is add function because you know that psi of minus x is equal to minus psi x. In the negative x direction. So I have derived this also in my theoretical lecture. That is k. In this case, k minus k cot ka is equal to kappa. With this understanding, we will move further. So we have seen in the positive x direction k tan k is equal to kappa. Now, in order to make dimensionless parameter, you multiply both sides by a, because the dimension of k is 1 over length, so a is length, so this will become dimensionless. Naturally, the argument of sinusoidal term must be a dimensionless because we are writing it in power series. So this can be written as Ka tan Ka, which is equal to kappa Ka. This Ka you can keep as Z. This Ka is equal to Z. This kappa A is equal to eta. So we know Z is equal to Ka. For this, kindly refer my theoretical lecture, which is equal to square root of 2me over h cross squared A. And eta, that is kappa multiplied by A, is equal to square root of 2m v naught minus E over h cross squared multiplied by A. Now you add z squared plus eta squared. So z squared plus eta squared, if you add both, if you square it, square root will get removed. Here you have plus e and here minus e. So which will get cancelled. You will get only 2m v naught over h cross squared multiplied by a square. This is taken as radius. So you know, by definition, x squared plus y squared forms a radius, which is equal to r squared. So this is equal to radius. So r squared is equal to 2m v naught over h cross squared a squared. So when r will increase, either this potential increases or the box length increases. So we can take z squared plus eta squared is equal to r squared, or eta equal to square root of r squared minus z squared. Here, why we are doing this is a transcendental equation. Z also contain eta, this z, and z also contain e. Sorry, eta also contain e. Both sides you have energy term, so naturally you cannot solve it analytically. You have to use the numerical method or graphical method. Here we are going to use the graphical method. So we got z tan z is equal to eta, and eta equal to square root of r squared minus z squared. And in the negative x-axis, we have seen the solution minus z cot z over which is equal to eta, and the radius is this one. When radius will increase, when the box length increases, radius will increase. When park's length, also when V naught increases, this radius increases. So what will happen if you have a depth, higher depth, potential is very high, then this is equal to one dimensional square well potential. You have more number of nodes, that is the odd bound, you have more odd bound state, sorry, more bound state, maybe odd or even more bound state when we not increases, that is in depth is very high, is equivalent to infinite square well potential. So when a squared increases, box length increases, then the radius also will get increased. Now you take this diagram. This is 0, pi by 2, pi 3 by 2, 2 pi, pi, pi 2, 3 pi. So now what is tan c? By definition, it is sine c over cos c. What will happen when cos equal to pi by 2 here? Cos pi by 2 is 0. So this will go to infinite. It will start from sine 0, 0, and it will start from 0 and suddenly increases to exponentially. This increases to infinite when z tends to pi by 2. This x-axis is z and y-axis we have some. Then this is equal to this curved line, which is equal to square root of r squared minus z squared. Then this solid line is for this tan c, because tan c, which will become the multiple of pi by 2, that is add multiple. So pi by 2, 3 by 2, and 5 by 2, you will have this solid line. You can see the solid line. So here you come to here, then when sine 0 or sine pi is equal to 0, you will get infinite. So when sine pi is equal to sine pi equal to 0, it start from sine pi by 2 is 1. So it start from pi by 2 and goes to infinite when it reaches the pi and 2 pi and 3 pi. It will go like this. If you draw the radius, this is the dotted line is minus z cot c. Solid line is z tan c. And this radius is square root of r squared minus c squared. From which edge we can find the intercept and find the result. For the add function, you can see when a squared is small and v naught also small, then you will have only one node, this one. That is even because it's a solid line. There is no odd bound at minimum energy level. Similarly, when radius increases, you have more node, including odd or even. This is even node and one odd node. Then again one odd node. You can have if radius increases, number of node also increases. Uh, so this is our confirmation. So you will get it will behave like one infinite potential when V naught is very high. Thank you very much for watching my video and supporting me continuously. Thank you very much.